Hello, everybody. It is my pleasure to open our seminar. The speaker today is Professor Geoffrey Penington. He will tell us about finding pitons in unexpected places. Jeff, please, 1 hour.
Okay. So thank you very much indeed for asking me to talk. So this talk is going to be based on a paper that came out a couple of weeks ago, I think, a week ago, something like that, that was with Netta Engelhardt and Arvind Shivaji Mogadam, which is obviously called Finding Pythons in Unexpected Places. And in many ways, it's a spiritual, if not sort of technical follow-up to a paper we put out earlier in the year called A World Without Pythons Would Be So Simple. So what is the idea of this talk? Well, in the last couple of years, we've had this sort of huge progress in understanding how information gets out of breeding black holes. And there's this whole story there. And really, this actual talk is not going to be about that. It's going to be about non-evaporating black holes and what happens to them, which will turn out to be similar, they're slightly different. But just to get people up to speed, I feel I should give a sort of quick summary of the story for evaporating black holes, which really it was started at least with 2 papers in 2019 that came out at the same time, one by me and one by Almiri, Engelhardt, Mauff, and Maxfield. Okay, so how does that story work? What happens for evaporating black holes? Well, if we have a black hole in ADS and we want it to evaporate, then we need to do something to it, right? Black holes in ADS, unless they're really tiny, just sort of sit there in equilibrium with their Hawking radiation. So in order to make it evaporate, what one does is one turns on a coupling between the boundary of ADS and some other system. So we have sort of some interactions going on between here and here. I've drawn this other system as just sort of a second copy of ADS, but it can really be anything you want. It can be some completely non-gravitational system. It can be basically anything. So what does this coupling do? It means that rather than this sort of Hawking radiation coming out, hitting the boundary of ADS and being reflected back into the black hole, which means that the black hole won't actually lose energy, then instead it's able to basically travel through the boundary, or at least there's some probability that it does, and the information and the energy ends up escaping into this second system. So it's a pretty generic phenomenon as long as we sort of don't have much any energy sitting in the second system, and we couple in a way that conserves the total energy in the two sides, we're going to get an energy flux flowing across this surface. Okay, so what's the effect? Sorry, I'm getting some background noise. Is someone asking something, or? Okay, I think we're good. Okay, so what happens when we couple the copy of the black hole in ADS to a bath in this way? Well, the answer is, if you look at the state of the original black hole at some time after we've turned on this coupling for a while, then there's what's called a quantum extremal surface, a non-trivial quantum extremal surface that sits actually in the interior of the black hole. It actually is sort of, let's see, I can draw this here. It's a order G Newton radius inside the black hole horizon. And it's sort of, if I draw a dotted line back here, it's order a scrambling time in the past of this this time where we're computing this quantum extremal surface. So what is a quantum extremal surface? Well, physically, it's just a surface that's a sort of local extremum of what's called the generalized entropy. So the generalized entropy of this red surface is just its area divided by 4 times Newton's constant, plus a quantum correction to the area, which is just this S bulk here, which just means the entropy of all the bulk fields sitting in this black region between the quantum extremal surface and the boundary. Okay, so practically that's just the definition of a quantum extremal surface. But the important point for caring about the information paradox and so on is that there's this rule originally introduced by Engelhardt and Moore called the QES prescription, which is a generalization of an earlier rule called the Ryo-Takanagi formula. And what that says is a couple of things. Firstly, it says that the generalized entropy of this surface, or of the smallest quantum extremal surface, is equal to the entropy of this Hawking radiation that we're trying to compute the entropy of. So that's one thing it says. And in fact, if you look at what that says about the entropy of the Hawking radiation, you find that really there's two quantum extremal surfaces. There's the one that I drew, and there's also another one which is just the empty surface. And before the so-called page time, when the black hole has less than half evaporated, it's the empty surface that has the smallest generalized entropy. And so that controls the entropy, and it just goes up and up and up linearly, like Hawking would have suggested. But then after the page time, this new quantum extremal surface has the smallest generalized entropy. So it starts getting back down and exactly follows the page curve. But this quantum extremal surface also has other consequences, which will be more important for our purposes. And the biggest one is that it tells you what part of the bulk can be reconstructed from which part of the boundary.
Excuse me, Jeff.
Yes.
Can I ask you the question? What do you mean quantum corrections to area? Quantum
gravity? I literally just mean this term S bulk. So it literally just means the bulk entropy of we have quantum fields in this bulk spacetime, right? And we can look at the quantum fields just on this black region here between the quantum extremal surface and the boundary. And those quantum fields have a von Neumann entropy. It's actually formally infinite, but it gets renormalized by the area term. And we're just going to add that into the area. So we have area over 4G. It's more like a quantum correction to the Bekenstein-Hawking entropy.
Is there a divergence there?
Say that again?
Are there divergences there?
I couldn't. Sorry, say that again.
The question is, are there some divergences there?
Oh, yes. So these two terms are both individually divergent. So this von Neumann entropy is infinite because you have effectively you have Rindler modes really close to the edge of the region, and they're like thermal modes, and they contribute entropy, and you get an infinite amount from UV modes closer and closer to the surface. But this A over 4G is also infinite because the Baire-Newton's constant is formally infinite. And it turns out that they renormalize one another. So this full combination, the generalized entropy, is actually UV finite.
Okay, thank you.
Good. Okay. So it turns out that there's a rule called entanglement wedge reconstruction that you can derive. And what it says is that everything to the right of the minimal quantum extremal surface, so in, say, a wedge that looks like this, is encoded. So I can reconstruct it, I can recover it by looking at the boundary state on this boundary. On the other hand, everything to the left of the minimal quantum extremal surface, so a wedge that looks like this, is encoded in this second auxiliary system, which is the system containing the Hawking radiation. So it's encoded in the Hawking radiation rather than being encoded in the original system that described the black hole. Okay, so that's after the page time. Before the page time, this wasn't the minimal quantum extremal surface. The minimal quantum extremal surface was empty. And so the whole interior was effectively to the right of it, and everything was encoded in the original black hole. The Hawking radiation genuinely just looked like thermal noise that didn't tell you any useful information. Okay, so that's the sort of main traditional part of the story. There's a second part of the story which is going to be important for what I'm going to say, which is that both before and after page time, if you want to recover information that's sitting in this interior of the black hole, deep in the interior somewhere, by looking at the state of the boundary, so either the state of the Hawking radiation after the page time or the state of the black hole before the page time, then to actually recover that information is exponentially complicated. By this, I mean roughly that it's e to the something of order the entropy of the black hole. Okay, so this is incredibly hard to pull out this information. And this part of the story also comes from the fact that you have this QES sitting here. And this comes back from a paper with Brown, Caribbean, me, and Lenny Suskind from December 2019, which was called the Python's lunch. And I'll tell you a lot more about what a Python's lunch is and why in a bit. But first, I want to sort of introduce the main theme of this talk, which is basically going to be, what about non-evaporating black holes? So we have this whole story that explains a lot of things when black holes are coupled to this extra bath. But at least naively, that story doesn't seem to say anything about what happens if we just have a black hole sitting in anti-de Sitter space, not doing anything much. So as I said before, if we don't have this external bath, then the Hawking radiation, there is Hawking radiation still. It goes out to the boundary, but then it just bounces back in. And so the energy is conserved. You don't have any energy loss over time. The black hole just sort of sits there. There's another thing that's true, which is if I look at the boundary time, say here, and I want to look for a quantum extremal surface associated with this boundary, then there's actually a theorem that any such quantum extremal surface can't exist. And it can't exist for a very simple reason, just if we had a quantum extremal surface in this space-time, it would be causally separated. So we could go back along a past light cone and get out to the asymptotic boundary over here. Okay? And this asymptotic boundary, this is true even if we have sort of isolated evolution of the boundary conditions, no coupling to an exterior system or anything like that. And there's a sort of widely believed conjecture with very strong evidence for it called the quantum focusing conjecture that basically just says that can't ever happen. Okay? So this space-time cannot have a quantum extremal surface sitting in the interior of the black hole like we found for the evaporating. So you might say, okay, that's fine. It's not evaporating. We have no information paradox in the same way. And to some degree, that's true. You don't have a page curve or whatever for this black hole. It's just sitting there, and the entropy is zero all the time. But there's still some very weird stuff going on. There's still some stuff that looks like weird black hole physics, like you might get in an evaporating black hole. So what is that? Well, the first example is, let's say we look at some mode, some partner of a Hawking pair. So we had this Hawking mode that came out here, and it has some partner that's up here. And let's think about what would happen if we tried to reconstruct that partner on the boundary here. Okay? Turns out there's very good reasons based on sort of simple toy models to think that doing so is still exponentially complicated, just like we found for the evaporating black hole. It's still really hard to be able to find an operator acting on the boundary that sort of in the bulk acts by changing this mode. And basically the reason for this is that the naive way you would do that is you just sort of evolve backwards in time, wait until this mode sort of ends up coming out to the boundary, and then reconstruct it. But as you evolve this interior mode back in time, it gets blue shifted and blue shifted and blue shifted until it becomes transplanckian, and then it doesn't make sense to talk about reconstruction. So that just sort of doesn't work. And instead, it seems like it's in fact exponentially hard to reconstruct. And there's another aspect which I won't talk about so much, but this interior partner also appears to be state dependent. And what that means is basically that the way you reconstruct it on the boundary has to depend on the black hole microstate that you have. And so you can't just find one size fits all reconstruction that works for sort of any black hole microstate. You need to restrict to some code subspace of states, some select set of states that the reconstruction is meant to work. So both of these things are very explicitly sort of hallmarks of what happens when you're trying to reconstruct something, but it's behind a quantum extremal surface, right? I already said that this exponential complexity is something that happens in evaporating black holes, and it happens because of this quantum extremal surface. What is going on here? Where we apparently don't have a quantum extremal surface, but we're still seeing the same effect. So let me make that sort of tension a bit stronger by talking very, very briefly about my paper with Netta Engelhardt and Arvin from back in February this year, which I believe Netta actually gave a lecture on in this seminar series about a month ago. So I won't talk much about it. But what we did there is we argued that in the classical limit, where you can treat the bulk physics as completely classical, then it's actually easy to reconstruct. We were basically able to prove that it's easy to reconstruct any operator that's not behind an extremal surface. And by easy, I mean that you can do this sort of time evolution back and forth on the boundary and eventually pull it out to the boundary and then do a simple reconstruction. So this really starts to seem like a tension because we've proved that there's no QES in the spacetime. We also have very strong reason to know that reconstructing this interior partner is exponentially complicated. And here we're claiming that never happens, that when there's not an extremal surface, the reconstruction is never exponentially complicated. Of course, there's one possible loophole there, which is this proof was classical, whereas this effect is very, very quantum, right? Like this trans-Planckian physics getting involved, that's something that can only happen when you have quantum fields. With classical fields in the bulk, it just wouldn't happen at all. So you might say, okay, you guys proved that that's true classically, but quantum mechanically, it's just totally different. So that would be one possibility, but that's not what we claim in this more recent paper. What we claim instead is that this exponential complexity of reconstructing this mode deep in the interior of the black hole does come from a quantum extremal surface, but it's a quantum extremal surface in a different state to the sort of state we have here, where I claim there couldn't be a quantum extremal surface.
Excuse me, what kind of information you want to reconstruct?
So
what is given on the boundary, what you want to find?
We want to reconstruct the state of this mode that's a partner of a Hawking mode. So we want to basically, you can think of it as like extracting a qubit that's sort of maximally entangled with this qubit describing the Hawking mode.
Do you want to find the wave function of a particle inside a black hole?
Yes, essentially, but of a particular mode inside the black hole. So we want to be able to like measure an operator acting on this mode deep inside the black hole that's a partner of a Hawking mode. Is that clear?
You make measurement on the boundary.
Yes.
Right?
Yes. We want a boundary measurement that in the bulk acts as a measurement on this interior.
What do you measure on the boundary?
It's going to be some complicated boundary operator that is related by the ADS CFT dictionary to this bulk mode in the interior of the black hole.
Okay, thank you.
Okay. Thanks a lot for the questions, by the way. It's very helpful to have these. Okay. So as I say, my sort of central claim of this paper and this talk is that even though I just told you there couldn't actually be a quantum extremal surface for this particular state that we formed just by forming a black hole from collapse and just letting it sit there for a while, that's not actually the right state to be considering to determine the complexity of this interior operator. Actually, we should be considering a different state, which is, okay, let me define it quickly now. If we want this reconstruction to work not just for sort of the original state we started with, but for a whole code subspace of states, right? In the original state we started with, this interior mode is just maximally entangled with the Hawking mode outside, and we can't do anything to it. So we need to introduce a code subspace of states, and then it turns out the right state to consider is going to be a maximally mixed state on that code subspace. That maximally mixed state will have a quantum extremal surface, and that quantum extremal surface will explain the exponential complexity of the construction. Okay, so that's the very brief version of how the story is going to unfold. But before I actually get to that, I want to spend a bit of time talking about this Python's lunch conjecture, why a quantum extremal surface has anything to do with exponential complexity, so that hopefully we can see why this maximally mixed state is going to get involved and how the story is going to go. Okay, so this is going to be talking about this paper from 2019 with Adam Brown, Hrant Gropian, and Lenny Susskind. And basically what we did in this paper is we used this widely believed analogy between bulk states in ADS-CFT and what's called tensor networks. So a tensor network is just a sort of graphical representation of some complicated set of tensors where each line represents an index of a tensor, each blob represents a tensor, and lines that go between two tensors are indices that are contracted. Ones that just sort of left dangling are leftover indices of the full tensor produced by this network. Okay, so the idea is that this big tensor network that sort of looks like, has a lot of legs over here on the left, then a small number of legs, then bigger again, then smaller, then really big, is sort of analogous to a bulk in ADS-CFT that looks like a wormhole that gets small and then has a bulge in the middle and then gets small and then gets bigger again. Okay. So in this tensor network, the equivalent of a quantum extremal surface is sort of a minimal cut, a locally extremal size cut in this tensor network. So we have one over here, sort of, it's a cut separating the left end from the right end. So this one over here is the smallest cut through the network. So that's the minimal QES. That's the thing I claimed that determines things like the entanglement entry, right? So in the tensor network, it's pretty easy to see that the entropy of the state, entanglement entropy between the left-hand end of the quantum state this produces and the right-hand end, which corresponds to the boundary state in ADS-CFT, is just given by the number of legs, basically, in this minimal cut through the network. Then in the middle of this bulge, we sort of have a max cut that I've called gamma bulge. That's sort of the largest point that the cross-section reaches. And then further along, it gets smaller again, never gets quite as small as this sort of minimal cut on the left, but it has a sort of local constriction. And that I'm going to call the appetizer QES, or gamma appetizer. Okay.
So Jeff, can I ask a question?
Yep.
Can we observe something like a Python lunch in a continuous version of tensor network renormalization, like Chimera or something like that, for example?
That's a very good question. I haven't thought about that. I encourage anyone to think about that question. I would assume so. Yeah, I mean, it would just involve C-mirror you can think of as some almost like Euclidean time evolution or something like that, right? And so it would just sort of involve forwards and backwards Euclidean time. Yeah. Oh, I would assume the answer is yes, but I have not explicitly thought about it.
Okay.
Okay. So it is a fact that if I have a tensor network like this, then for generic tensor networks, which are believed to be the ones corresponding to gravity, then you have a sort of isometric map from the legs in this minimal cut, plus these extra legs that I've drawn of dots coming out of the page, then these extra legs are basically going to correspond to sort of the bulk fields in that region of the bulk, all the way out to the right boundary. Okay, so yeah, actually we need a particular condition for that to be true. We basically need the size of this minimal cut here on the right, which I call the appetizer surface, to be larger than the size of the minimal cut on the left, plus all the extra bulk legs that got added in the middle. As long as you have that condition true, then generically the map from this sort of left minimal cut plus all the bulk legs all the way out to the right boundary is going to be an isometry. What that means is that if we haven't...
Sorry to interrupt you, Jeff. Is it really an isometry in the sense of quantum information theory?
Yes.
That the fidelity with...
it's an isometry in the sense of V dagger being roughly equal to the identity, where V is the, yeah. Does that answer your question?
Well, it answers the question, although I'd be happy to know in what sense it's close, but I don't want to interrupt you more.
Yeah, I think most senses it's close. Essentially, yeah, if you're wanting the exact statement for like a random tensor network or something like that.
Yes, you can tell me some other time.
Yeah, I would have to think of a nice statement, but yeah, any reasonable sense, I think it will be close.
Anyway, your claim is not that there's any intrinsic unitarity here, but that simply...
My claim is that with sufficiently random tensors, then just the size differences, the fact that we have sort of more legs here in this cut on the right than we did in the cut on the left, plus everything extra that got added in the middle, is enough to ensure that basically all the information gets through. There's enough room for all that information, and randomness is sufficient to mean that.
So it could be intrinsically completely non-unitary, but nevertheless, when the tensor is growing, when the network is growing, it'll behave as if it's unitary.
Yeah, basically. I mean, this is closely related to the fact that a random state is close to maximally entangled.
Thank you.
Okay. Okay. So, okay, the fact that we have this isometry from local isometry from this minimal cut plus bulk legs to the boundary basically tells us that if we have some operator we want to apply to one of these bulk legs, we want to change something about the state in the bulk, then we can do that by applying to the, so if the V is the map to the boundary, then we just apply O bulk, V dagger, V. That's an operator acting only on the right boundary that will do the same thing as the operator in the bulk that we want to apply. Okay, so this is the tensor network version of having entanglement reconstruction, of having everything to the right of this minimal cut be reconstructable, just using the right boundary. On the other hand, even though, the complexity of this isometry V can actually be much, much larger than the sort of size of the network that describes it. So this is a slightly weird phenomenon, so it's worth taking a minute over it. So remember that even though the entire map from the minimal cut plus bulk legs to the right boundary was an isometry, these individual tensors, as I was saying to Edward, are not isometries. Okay, so in particular, for example, let's take this tensor here, right? That has two input legs on the left, only one output leg on the right. So clearly it's not a unitary or an isometry or anything like that because the input is bigger than the output. Okay, it forms part of an overall isometry from these input legs plus the bulk legs to the right boundary, which is really large, but just viewed on its own as a linear map, then it's not isometric. Okay, so what does that mean? It means if we want to implement this isometry V by doing some sort of unitary circuit, by doing unitary operations on our right boundary, then we can't just do it by sort of implementing this tensor, then going through the tensors one by one. It's actually a much, much more complicated process. Okay, so this is where the fact that we had this sort of second constriction was really, really important. If the tensor network just got larger and larger as you went from left to right, then each individual tensor would effectively be an isometry. So you could just implement them one by one and the complexity would be really simple. But because we have this second constriction, then that sort of trivial way of implementing the isometry just doesn't work, and we need to come up with something clever. In fact, there's no efficient way to do it at all. Yeah, basically what's happening here is we have some tensors that have a bigger output than input. They're isometries effectively, but we also have some tensors that have a smaller output than input, and they're like an isometry going the other direction. Okay, so they're like an isometry going from right to left, or the adjoint of an isometry going from left to right. And what that looks like at the end of the day is you're trying to do some relatively simple unitary that describes the sort of unitary processes of each tensor network. But then you have some tensors that are adding in extra degrees of freedom, the ones where the tensor network is getting bigger. So that's like adding in some extra ancilla qubits in some fixed state. Okay, so we've added in m extra qubits here. But then you also have the tensor networks where the size of the output is getting smaller, and those correspond to the adjoint of adding in qubits, which is post-selecting qubits onto some, like just insisting that those qubits end up in the particular state, and just forcing them to be in that state, and then just looking in the output on the remaining qubits. Okay, so what we're trying to do is take this simple circuit that sort of cheats by doing this post-selection and turn it into a circuit that doesn't cheat and just starts with the input and ends up with the output. Turns out there's a way to do this. There's a quantum computing algorithm that basically does exactly this. It's called Grover search. It's one of the two algorithms that ever get used. But it also turns out it's really, really hard. In fact, the time it takes is exponential in the number of qubits that you want to post-select on. So if we have like n qubits that we're going to post-select on, then it takes a time that's order 2 to the n divided by 2. Okay. So we basically, in the paper with Lenny and Adam and Grant, we basically said, okay, that's how things work in tensor networks. Let's just assume that gravity works exactly the same way. So we made this conjecture called the Python's lunch conjecture that says that in gravity, the complexity of reconstructing something behind a quantum extremal surface is just given by half the exponential of the difference in generalized entropies between like two non-minimal quantum extremal surfaces, this sort of bulge surface and this non-minimal constriction to its right. Okay, that difference tells you the number of qubits that need to be post-selected. Crucially, however, the number of qubits that need to be post-selected is given by the difference between the generalized entropies in the maximally mixed bulk state. Okay, that's really because you have these bulk input legs to the tensor network, and those contribute to the number of qubits that need post-selecting. Right? If my input is all these legs going through the network, those are like area contributions, and also these extra bulk legs that are sticking out of the page, whereas my output is just these legs going through the constriction. Okay, so the number of post-selected qubits includes the entropy of these bulk legs, which is basically the entropy of the bulk fields if they were in their maximally mixed state for that particular code subspace. Okay, so we're now finally ready to talk about these non-evaporating black holes that we started with before. Hopefully it's clear from that story about the Python's lunch that at the end of the day, if we want to know the complexity of reconstructing some interior outgoing mode here, sorry, I don't know why I drew a new one. I just meant this blue mode here. Then we first need to define a code subspace where that blue mode is allowed to be in any state it likes. It's not forced to be maximally entangled with the Hawking mode, even though that's what happens in practice if you just make a black hole from collapse. Then we want to allow it to be in a random state so that we can actually do things to it. Right? It's like one of the bulk legs in the tensor network that we can fiddle around with and change the state of. once we do so, then the right state to consider in order to work out whether there's a Python's lunch and work out the complexity of reconstructing things is a state where it's the maximally mixed state within the code subspace. In other words, it's a state where this interior mode is completely disentangled from the Hawking mode. Okay, this is a bit of a weird state. It's not one we often consider because we normally think about states formed from collapse. But it's the right state if you want to work out the complexity of reconstructing that operator, even if eventually you're going to act with that operator on the maximally entangled state. Okay. Any questions about that? Because that's really the central point in this talk. It's just the fact that that is the right state to be considering rather than the original state we had. Okay, cool. So now all we need to do is show that unlike the state formed from collapse, which I could prove trivially didn't have a quantum extremal surface, then this one does. And that quantum extremal surface is the cause of this exponential complexity. Okay, so what we're going to do is we're going to take a surface that's sort of sitting slightly inside the black hole horizon. It's sort of sitting around where this disentangled mode is. And then we're just going to sort of parallel transport that surface back into the past. Okay, and we're going to keep parallel transporting it till it gets roughly a scrambling time into the past. Now we're going to look at the quantum expansions of that surface. We're going to look at the quantum expansion in the sort of future outwards going direction. I'm going to call that theta L, and also in the past outwards going direction. By quantum expansion here, I just mean the gradient of the generalized entropy. Okay, so because the surface is inside the horizon, it shouldn't be surprising to you to hear that the quantum expansion in the future outwards direction, this thing theta k, is less than 0, right? That's just telling you that this surface is like a trapped surface or something. It's yeah, even if you try to head outwards away from the black hole, you find that you get smaller and smaller and smaller, and you hit the singularity. On the other hand, this past directed outwards going expansion theta L is initially just greater than 0 because the classical area as you go backwards in time and outwards just gets bigger. You're going outside the black hole, and the area term in the generalized entropy gets divided by Newton's constant, which is really small. So it sort of dominates over anything that might be happening with the bulk entropy term, and we have theta L greater than 0. But now we're going to take this surface, we're going to move it backwards and backwards along the horizon into the past. Okay, what happens then is that effectively L gets blue shifted, right? Like as we go back into the past, everything gets closer and closer to the horizon, and basically the area becomes roughly constant because everything is just the horizon area as we go far enough back into the past. It means the classical area gradient gets smaller and smaller and smaller, and in fact it exponentially decays over time. On the other hand, okay, so if the bulk fields were in the Harder-Hawking state, okay, if this interior mode was maximally entangled with the Hawking mode, as it usually is, or thermally entangled, then it turns out that we also get that the bulk entropy gradient goes to 0 as we go back into the past. And so in fact, the whole quantum expansion always stays positive, but it just gets smaller and smaller and smaller as we go back to it past infinity. However, we've now changed things. We've now disentangled this interior mode from the Hawking mode outside. What does that mean? It means we caused a sort of order 1 shift in the L gradient of the bulk entropy. So there's a sort of order 1 difference between the entropy gradient in the maximally mixed state and the entropy gradient in the Harder-Hawking state where they were maximally. But this order 1 entropy gradient does not sort of disappear as we go back into the past because these modes are getting blue shifted along with everything else. So they're also ending up closer and closer to the horizon. So this entropy gradient is just still there. It's just an order 1 thing that just stays there as we go backwards and backwards in time. Okay, so that means this quantum expansion in the maximally mixed state has to be order 1 less than the quantum expansion in the Harder-Hawking state, which I already claimed tends to 0 as we go back in time far enough. Hence, if we go back in time far enough, we must find that the quantum expansion of the maximally mixed state becomes negative. Okay, so that was a complicated story, but the takeaway, the too long didn't read, is just that if we take some surface that's slightly inside the horizon and that's more than a scrambling time in the past, then it's what's called antinormal, which just means that both these quantum outwards expansions, theta k and theta l, are going to be strictly less than 0. Okay, for this maximally mixed state in essentially any code subspace where you can excite this interior mode. Okay, so now we're starting to get somewhere. This is some new effect that happens in this maximally mixed state that didn't happen in the state that was just formed from collapse. But what we really need to find is an actual quantum extremal surface, right? That's a surface where we have sort of theta k and theta l equal to 0 rather than just strictly less than 0. Turns out there is one, but the exact location of where it is depends on details of exactly how you constructed this code subspace. And so it's a bit messy, and I don't want to get too deep into it now. But there's a very nice little general argument that tells you that having this surface where theta k and theta l are both strictly less than 0 is enough to basically prove that there exists some surface outside that with theta k and theta l both equal to 0. Okay, so an actual quantum extremal surface. So let's just briefly talk about how that argument works. So what do we do? It uses this thing called restricted maximin. So what we do is we consider some Cauchy slice going between this anti-normal surface over on the left and the right boundary. We then look for the surface within that Cauchy slice that has the smallest possible generalized entropy. Maybe it's this green dot here in the middle. Okay? And now we consider every possible Cauchy slice rather than just one. We consider every possible Cauchy slice going from this anti-normal surface to the right boundary. We look at all of them and we maximize the minimal S-gen surface across all those different Cauchy slices. Turns out this is a well-behaved thing. This ends up being a nice smooth surface. And given we've sort of maximized in time-like directions and minimized in space-like directions, then the resulting surface basically has to be extremal unless it's somehow ended up sort of stuck against the boundary of the allowed region. Maybe it's stuck like light-like separated from this surface, or it's stuck like touching this original surface on the left. In that case, it's allowed to not be extremal because you can't sort of vary it, and you know, it can be, you know, if something's on the boundary of the allowed region, then it doesn't have to be a stationary point to be a minimum or a maximum. But it's pretty easy to show that a sort of minimal surface within some Cauchy slice can't be touching this left boundary, this anti-normal surface gamma, because theta k and theta l at gamma are both less than 0. And so you could always get smaller generalized entropy by moving it a little bit away to the right of the surface gamma. Okay, so we can't have that problem. And it turns out that it also can't be sort of light-like separated from that surface gamma. Again, you need to use this quantum focusing conjecture I've mentioned before, but it all goes through. Okay, so this surface always has to be space-like separated from gamma. That means it always has to be extremal. So just by finding this anti-normal surface gamma with theta k and theta l strictly less than 0, we've proved the existence of a quantum extremal surface outside it with theta k and theta l.
Jeff, may I ask a question?
Yeah, absolutely.
Can you say that quantum extremal surface is unique? Maybe some situation
I'm afraid
that
you're breaking
it
up.
can be
Possibly I'm breaking up.
degenerated.
I'm afraid I missed most of the question.
Are you sure about uniqueness?
Uniqueness?
Yes, the question of uniqueness of quantum surface, extremal surface.
Okay, good. So there definitely is more than one extremal surface, and in fact, it's important there is. So if we go back to to this sort of tensor network, right? We had one extremal surface like here, okay? We had that was the sort of minimal surface that determined how much could be reconstructed. Then we had this second one at the other end of this sort of bulge. Okay, that was determined when, so everything to the right of this was simple to reconstruct, everything to the left of it was complex to reconstruct. And then we also, in fact, had this big one in sort of the middle of the bulge. And that big one helped determine like how complex it is to reconstruct stuff in this bulge. Okay, so there's definitely more than one extremal surface. Generically, there will be a unique minimal one, just because you'll have some set of extremal surfaces with different generalized entropies, and one of them will have the smallest generalized entropy. Also turns out that there's always a unique outermost extremal surface. So there's always a extremal surface that's nearer to the boundary than any other extremal surface. So we don't get like an extremal surface here and an extremal surface here, unless there's also an extremal surface, say, over here. Okay?
Okay, thank you.
Okay. So yeah, so that's very helpful lead into the thing I was going to state now, which is to sort of lay out, okay, so what does this whole Python's lunch actually look like in the evaporating black hole? So I just claimed in a tensor network, we have three extremal surfaces. Okay, we have one that's sort of, yeah, so what do these correspond to in the non-evaporating black hole? Sorry. So one of them is just the empty surface. So I can draw a dot here, just as a surface containing no points, right? This is r equals 0. Okay, so that's the sort of that's the equivalent to this minimal cut here. It's just completely empty. We don't have a left boundary at all. We only have one boundary in this case. Then we have a sort of maximum size of the bulge, and then it gets smaller again, and there's the constriction. So where are those? Turns out, so the constriction, so our constriction we knew had to be outside this antinormal surface, right? So the antinormal surface that we found was like here. Okay, so the constriction has to be outside that, so it's out here. So roughly speaking, it's on the right-hand edge of the interior modes that we disentangled, the interior modes that we wanted to be able to reconstruct. And finally, yeah, and it's one scrambling time in the past of whatever boundary time you're trying to do this reconstruction. Sorry, it's one scrambling time in the past of whenever the last disentangled Hawking radiation escaped. Sorry about that. And then finally, there's this gamma bulge surface. This is the sort of maximum cross section of where the bulge gets as large as possible, and that sits on the left-hand edge of all the interior modes that you want to be able to reconstruct. And in fact, it's sort of further in the past. It's in fact where it's sort of at the time when the black hole was formed from collapse. So this is the collapsing matter forming the black hole. And this gamma bulge surface basically sits in the collapsing matter. Okay. So knowing roughly where those surfaces are, then we can compute the size of this lunch, and that, remember, determines the complexity of doing this reconstruction. And it turns out that the size all comes from the difference in S bulk, and it's basically determined by how many of these interior modes you've actually included in your code subspace. Roughly speaking, it's 2 times the number of interior qubits that you included in your code subspace. And so that means that the final answer for the complexity of reconstructing these interior modes depends on how many different modes you want to be able to reconstruct, how large a code subspace you're doing the reconstruction for, but it's order 2 to the number of qubits, interior qubits that you want to be able to reconstruct. Turns out this gives exactly the same answer you get by doing calculations in sort of simple time models of quantum circuits, and just looking at the complexity to sort of distill out a purification of some qubits that represent Hawking modes. So this is the right answer that we should expect. Okay, so that's really everything I want to say. That's hopefully given you the big picture of what the story is for non-evaporating black holes, why they're still mysterious, even though they're not evaporating, they don't have a page curve, they don't have quantum extremal surfaces, at least if you don't try and reconstruct anything. But I want to very briefly mention a different paper that was by some computer scientists, Adam Buland, Bill Pfefferman, and Umesh Vazirani. And they considered a slightly different setup. So what they considered making a black hole from collapse, and then they applied some sort of random simple operators, the Hawking modes, that were out near the boundary, and sort of let them fall back into the black hole. And they did this over a long period of time. They applied a load of different random choices of simple operators. And then they claimed that the resulting set of states you get is sort of, the individual states are exponentially hard to distinguish from one another. They're what computer scientists call pseudo-random. It turns out that exactly the same story I just told you sort of goes through in this case. The individual states in that set have no quantum extremal surface because they're just a black hole formed from collapse with certain boundary conditions. But if you look at the ensemble formed by all of those states, then that mixed state in the bulk does have a quantum extremal surface, and its size gives the expected complexity the BFE span. So that's just another example of similar confusions people had about why is this thing so exponentially complex to reconstruct that get resolved by the same phenomena of a quantum extremal surface, and hence a Python's lunch, appearing once you consider the right code subspace, the right set of states. Okay, so that's really all I have to say. So let me just say 3 sentences. So hopefully, if you found the rest of the talk unintelligible, you can at least know what the rough takeaway was meant to be. So the big point is that non-trivial quantum extremal surfaces, these special quantum extremal surfaces sitting in the horizons of black holes, are not just something that happens when you couple a black hole to a bath. They're not just something that happens for evaporating black holes. They really very generically explain the sort of weirdness of interior reconstruction in ADS-CFT. So even for non-evaporating black holes, QESs are still the obstruction to reconstructing these interior modes. It's just to see the QES, you have to go to the maximally mixed state of the code subspace you want to do the reconstruction for. And normally we were considering a particular state in that code subspace that was the black hole formed from collapse. But implicitly, by even wanting to talk about acting with an operator on those interior modes, we were really thinking about the whole code subspace. We just weren't explicitly recognizing that we were doing so. So yeah, just by looking at the sort of quantum geometry, the geometry plus the entanglement structure of the bulk fields in these states, you can just literally read off the difficulty of reconstructing the interior of a black hole. You get very precise agreement with toy models when you do so. Everything works out pretty nicely. Yeah, any questions? I think there's a couple of hands raised in the chat.
Okay. Thank you very much. Thank you very much. Questions, please. The first question comes from Igor. Igor, please ask me a question.
Yes, thank you very much, Jeff, for a very nice talk. I am worried about the meaning of reconstruction prescription. Let us consider the simplest case of the not black hole, but black body, is Planck distribution for photons, gravitons, and so on.
Yep.
What will be your prescription to reconstruction? What we need to measure?
Yeah. Okay. So let's say we have. Let's just talk about this a bit. So let's say we have some sort of bulk operator, O bulk, that we want to reconstruct. Okay. What do we mean by that? So on the boundary we have some whole CFT of states. Okay. And most of those states just look like some giant black hole or something like that. This sort of O bulk is not even defined for all of those states, right? So to even talk about measuring O bulk, we first need to specify the set of states that we're interested in. Maybe it's states with that particular geometry with like low energy excitations of bulk fields or something like that. Okay, so what you do is you specify a set of states that people normally call H code because the language comes from the language of quantum error correcting codes. Okay, so this is some subspace of HCFT for which this operator O bulk is defined, and you want to be able to reconstruct it for. Okay, then we can ask what it means to do a reconstruction. So a reconstruction of O bulk just means some boundary operator O boundary. Okay, such that O boundary acting on any state psi that is contained in this code subspace H code is the same thing we would get by acting with O bulk on the same state psi. Okay, and maybe we allow some small error there, but yeah. Is that clear? Okay, so then it should be clear that if we change our code subspace, then it changes maybe whether this is possible. It changes like which of these operators O boundary will work. And maybe you can get by with a simpler O boundary, or maybe you need to use a more complicated O boundary. So for the black hole, we could consider a code subspace where basically the state of everything is fixed, except the say one Hawking mode is allowed to be in an arbitrary state, and its interior partner is also allowed to be in an arbitrary state. Okay, so that would, let's assume that these are like fermionic modes. They have two states. So that would then be a four-dimensional subspace H code. So then we would need a boundary operator, O boundary, that acts the same way as the bulk operator on that four-dimensional subspace. We could also imagine a different code subspace where we include, say, two Hawking modes and two interior partner. Now we have a 16-dimensional code subspace. Our O boundary needs to act the same way as O bulk on the full 16-dimensional subspace. That's harder because it has to act correctly on more states. It ends up meaning that it's a more complex operator.
Jeff, I wonder if the following explanation would be clearer to some people.
Yep.
Instead of saying you want to start with the code subspace, you might say the following. You start with the actual black hole that formed from collapse. Then what you mean by reconstruction is you want, as an outside observer, to be able to demonstrate that you have the ability to do the experiments, on the Hawking quanta and manipulate them as you wish. So what would it mean to demonstrate that? You'd like to find if there are n quanta you're interested in, n operators that can flip, for example, the polarization vector of those n quanta. If you've succeeded, you will have been able to generate 2 to the n states by acting with those operators. So rather than saying that we can't have the discussion before we work on this code subspace, I think some people would find it more intuitive if you said, what we're aiming for is to develop the ability to manipulate Hawking quanta behind the horizon. If we've demonstrated that ability, we can then create this code subspace, and then you can analyze it from there.
Yeah, absolutely. I completely agree with that explanation.
Thank you. It looks like the existence theorem. For instance, if I want to derive the state equation of matter inside black hole, what I have to do practically?
Yeah, okay, so that's a good question. And the trouble with that question is that you sort of have to assume the state of the interior in order to work out how to reconstruct it on the boundary, at least the ways we know to reconstruct it on the boundary. And so I would say with the current tools we have, that's sort of hard to do. I feel like I'm not answering the question the way that would be most helpful to you, but like, yeah, essentially we're assuming that the interior of the black hole is, these interior modes are the things that are purifying the Hawking modes in the state formed from collapse on the boundary. And then we're finding like boundary operators that purify the boundary Hawking mode. That's the best answer I can give. And so, if your question is how do we know that the Hawking answer for what the interior of the black hole looks like is right, then these calculations sort of aren't telling you that because they're sort of assuming them.
I mean, the simplest thing. We don't know in advance the relation between pressure and density of matter. How we can reconstruct
what
it?
we do for I mean, if we don't know, then we would just need to consider a code subspace that includes all the possibilities, right? If we don't know very much, then we need a larger code subspace because we want to be able to account for more possibilities.
So you have to postulate a theoretical model of black hole, first of all, right?
Yeah, exactly. And you need that model to be sufficiently broad that you can cope with any of the possibilities. But normally, that's actually relatively easy to do if the black
And
hole.
what is your assumption about the equation of state you discussed?
So yeah, maybe we can talk about this offline afterwards because there's other people already ask questions and I don't feel I have a good quick answer that will satisfy you. Yeah, I mean, I'm sort of assuming throughout this that we know the bulk theory, and so we know the equation of state for stuff. What we maybe don't know is like the size of the black hole or something like that, and then we'd have to just consider a code subspace that can include different sizes of black hole. That's the best I can give you. I think we can talk about this more offline afterwards. Yeah.
Okay. The next question from Rukas Mountain, please. Ask your question.
Thank you very much. Can you hear me well? Or?
Yep.
Yeah. Oh, okay, good. Just general question. I was curious about possible applications of this to physical scenarios. I would say I feel that because this is strongly based on DLCFT, it seems to me, you cannot really apply to physical, for example, curved black holes. But eventually, you could try to apply to analog black hole. For example, in graphene, you can build very good analog of ETZ black holes, at least in principle. Not very easy, but can you comment a little bit on this?
Yeah. So I would agree. The stuff in this paper is fairly ADS-y because it relies on the stuff reflecting back in and also sort of the way we want to talk about reconstruction relies on the ADS asymptotic boundary. The evaporating black hole story I think basically works in flat space totally fine because you can just talk about what can you reconstruct from the Hawking radiation at asymptotic null infinity and things go through the same way. Regarding analog black holes, I think they just won't work in this way. And the reason for that is that the way you derive all these results in gravity is basically you do calculations that involve these things called replica wormholes. So space-time wormholes connecting different copies of your black hole in certain mathematical calculations. And those are very specific to quantum gravity, right? They're like an instanton effect specifically in quantum gravity, and you just won't have them in analog black holes. In analog black holes, you have they're like quantum field theory and curved spacetime, but they're not like quantum gravity. So I would say that you just wouldn't see anything like this in analog black holes. Lenny?
Oh, yes, Lenny, please, your question.
Oh, me?
Yep.
Yes.
Okay. Jeff, I have a riddle for you.
Yep.
Okay. What's the difference between a python's lunch and an island?
You've asked me this question before, Lenny. I think I answered you. I think, okay, let me give my answer. I feel like people use terms imprecisely all the time. I would say a Python's lunch is any time it's behind some quantum extremal surface. I would say, so it's a component of an entanglement wedge that's behind a quantum extremal surface. I would say an island is a component of an entanglement wedge that is classically disconnected from the rest of the entanglement wedge. As such, it's essentially, at least all the examples we know of are Python's lunches. So I would say an island is always a Python's lunch, but a Python's lunch is not always an island. Now, I know what your next response is going to be. And your next response is going to be, but it's not really disconnected because there's there's entanglement, and by ER
Yeah,
equals
yeah,
EPR,
yeah.
that means it's connected. And I would say, absolutely, I'm fine with saying it that way. And in that case, I would say that island is just imprecise terminology and nothing is ever really an island. And then you can maybe use island for anything that's Python's lunch, and sometimes people do. I would also point out that I think you invented the term Python's lunch in June 2019, and the term island was invented by AMMZ around the same month, and both papers ran out at the same time, and so to some degree they're just overloaded terminology.
I didn't ask this question. I didn't ask this question for any kind of political reason.
Yeah,
I asked it because I want to understand the two concepts.
I think in your language, given that you basically want to think of the A/4G term and the S bulk term as just completely interchangeable, equivalent, and you don't care about the distinction between them at all. And if you don't care about that, then I would say there's no difference.
Okay, so they're conceptually at least very, very closely connected. They're good. That helps me.
I would say that they're the same if you don't acknowledge that distinction.
Yeah.
And I just use the term Python's lunch when I'm thinking about complexity because it makes clear to people that it's following on from the history of our paper. I guess also the Python's lunch means we're like thinking about the set of three extremal surfaces, right? The one end, the biggest in the middle, and the other end. Whereas an island, normally you're mostly just interested in which one the minimal one is. Like, the terms are used in slightly different contexts normally, but they're the same.
The other thing is I actually was hoping to learn more about the connection with Bouland, Vazirani, and Pfefferman. You didn't have time for that.
Yep.
But I just wondered if you could say just a couple of more conceptual words about the connection. I mean, I find that a very fascinating paper, as you know.
Okay. So is the basic story clear to you, Lenny? Certainly the
Vazirani et al. Story is completely clear to me.
Yep. Okay. So they have an ensemble, right? Let's consider the maximally mixed state in their ensemble, right? So what has happened? There've been some Hawking modes that have come out to the boundary that have had a random choice of like Pauli effectively applied to them. Okay. Mm-hmm. In the mixed state where you just apply a mixture of those four choices of Pauli, what does it do? It disentangles that mode from the interior mode it was entangled with over here. Okay. Is that clear?
But,
if I start with
you're not making a measurement, are you?
No. I'm starting with the state like 0, 0 plus 1, 1.
Mm-hmm.
And then I'm applying. Okay, so we have a bra and a ket.
Mm-hmm.
Plus 1, 1. And then I'm applying with probability a quarter the Pauli xi
to
that thing. Okay. So they randomly choose a Pauli or the identity and apply it. Okay, what's the resulting state? It's just the maximally mixed state.
If you don't know what Pauli's you apply.
If you don't know what Pauli has been used, exactly. Exactly.
Yep.
Okay. So by applying this random choice of Pauli, if we don't know what Pauli has been used, then we've effectively created the same state that I was talking about earlier in the talk, where this interior mode is disentangled from the exterior mode. Okay. So that ends up creating a Python's lunch for exactly the same reason that it did in the talk. So what we end up having is we have
each instance of the ensemble, you don't have a Pauli.
Each instance you don't, right? Exactly. So we have this ensemble.
Okay, so how do we define? How do we define the geometry? How do you define the geometry associated with the ensemble?
You're worried about the back reaction being different?
No. I just want to know how each instance
it's pretty similar geometry for all the states in it, right? So it's really just the bulk state that is different in each case. Okay, as long as you do things that are small enough back reaction, then you just have a load of states that have the same classical geometry but a different bulk state. Then the sort of, if you don't know which state is in the ensemble, then you still have the same classical ensemble, but now you have a mixed bulk state. And we just look at that mixed bulk state and we look for a Python's lunch in that mixed bulk state, and we find one because we've disentangled the interior modes from the Hawking modes.
Okay, I don't completely understand it, but let's carry on the conversation offline.
Okay, sounds good.
because
Sounds good.
I'm missing
We
something.
can
Okay.
Zoom sometime or something.
Yeah. Okay.
Yeah.
Thank you.
Cool.
More questions, please? Yes, there are some questions. Misha Kramtsov, please.
Hi, thanks for the talk. So I want to ask the question. So why it is that when you in your setup, when you have the black hole not coupled to any external reservoir or anything, to deal with this Python launch, you have to introduce this ensemble structure already as a state. But like in the older studies of islands and so on, in the page curves, the kind of ensemble structure does not show up in this way. Do you have a conceptual explanation of why it happens this way?
Let me make a couple of comments about that. Okay, so one comment is that even in an evaporating black hole, if I go all the way up here, the code subspace does matter. So for example, I could consider a code subspace where I have a really large number of degrees of freedom sitting somewhere in here, where I don't know anything about the matter that formed the black hole from collapse, right? So in that case, if I don't know anything about how the black hole was initially formed, then I can't reconstruct stuff immediately after the page time from the radiation. And the reason for that is that in the maximally mixed state in that code subspace, then we have all this entropy from this unknown stuff that formed the black hole, and that makes the generalized entropy of this surface larger for the radiation, but it doesn't change the generalized entropy of the empty surface, and so it means that the island doesn't form yet for the purposes of doing a reconstruction on that code subspace. Okay, so the code subspace still matters even if the size of the code subspace still matters even if you're considering evaporating black holes. The difference obviously is that, okay, there's two differences. One, even if you just consider a single state, you still get an island forming. Why is that? Well, it's because in an evaporating black hole, you need to get a page curve, whereas for an isolated black hole, you don't have any, the entropy is just zero all the time, and so you don't need to have anything weird happening. The other thing is that for an evaporating black hole, you can consider a code subspace. So to talk about entanglement wedge reconstruction, you always need some sort of code subspace, right? But for an evaporating black hole, you could consider a code subspace that basically maybe includes just the state of some diary falling in like this, right? Say you want to think about Hayden Preskel. That's the thing you would think about, not one of these interior outgoing modes that look like this. For an evaporating black hole, even if you consider that code subspace, you still have an island because you had an island already. Whereas for a non-evaporating isolated black hole, then throwing something in, if the code subspace just involves the interior modes like that, then you basically, you don't have an island. You don't have a quantum extremal surface shows up, everything's fine. And the reason for this is just that for a non-evaporating black hole, if I throw a diary into the black hole and then evolve for some time, it's still easy to reconstruct that diary, right? All I have to do is evolve backwards in time, and lo and behold, the diary pops out. Everything's fine. Whereas if I throw a diary into an evaporating black hole and then leave it to evaporate for some time, then the diary ends up really, really exponentially hard to reconstruct from either the radiation or the black hole on their own, and so you still have an island. So the answer is it just comes down to the physics of the problem and when things are exponentially hard and when they aren't and stuff like that.
Okay, thanks.
Next question from Sravan, please.
Hi, with the QS description, how do you distinguish a supermassive black hole and a stellar mass black hole? I mean, with respect to the interior states, is there any difference or interior states?
Yes, so those would have very different classical geometries. And so in each case, if you had a quantum extremal surface, it would be at the horizon of the black hole. Those horizons will have different sizes, so they'll have very different areas. So the generalized entropy of the QES will be very different. There'll be a whole host of differences. Possibly you're asking a question of, say in ADS, we had like two different size black holes. We know it's one of the two and we want to distinguish which one it is. Can we do that easily? And yes, the answer is you can very easily. You just measure the energy. So yeah, if I have two very different classical geometries, then it's very easy to distinguish them. And in terms of how they behave individually, it's like there are obviously differences because of the size, but to a decent degree, a black hole is a black hole, and the basic story goes through in each case. Does that answer your question? I feel like I possibly.
I mean, whatever the size of the black hole, you're saying that interior must be the same in nature. I mean, that's what you're saying?
Oh,
well, I mean,
yeah, sure. I mean, the Hawking effect works the same way no matter the size of the black hole, right? Unless the black hole is really, really small. Yeah, so the basic story looks similar independent of the size of the black hole. The temperatures and the parameters will be different, right? The temperature will be different. The scrambling time will be different. All various different parameters will be different, but the qualitative story will be the same.
Okay.
Okay. The next question from Igor Volodych, please.
Okay. If you start from a collapsing matter in a pure state, then the von Neumann entropy is equal to 0.
Yep.
It should be 0 all the way if you have unitary evolution, not the page curve.
Yes.
What do you think about this?
Sorry, are we working in ADS here or in flat space or what? In ADS, it is certainly true, and it is true in all these calculations that if I have just a black hole formed from collapse, and it's not coupled to a bath or anything, it's just sitting there, then pure states evolve to pure states, and so it always has 0 von Neumann entropy. There's a sense in which it's like coarse-grained entropy increases, like its thermodynamic entropy increases, but its von Neumann entropy is always 0. Does that answer your question?
So, do you believe to unitary evolution in the black hole physics?
Yes, I would say so.
In such case, you should have 0 entropy for all time.
Yes, and that's what we find.
Okay.
Possibly something that may be confusing is that I'm saying that we have this non-trivial QES, and that QES has a large generalized entropy. Just to go back down to this, right? So for the non-evaporating black hole, what determines the entropy is the minimal QES, right? Remember? And for a non-evaporating black hole, that's always this empty surface that doesn't contain any points at all. And the generalized entropy of that for an isolated black hole is always 0. So even if there's other quantum extremal surfaces around, then the actual von Neumann entropy is always 0.
So the generalized entropy is a kind of coarse-grained entropy. Do you agree?
The generalized entropy is equivalent to the which entropy?
Coarse-grained, not fine.
Sometimes, yes. The generalized entropy of this surface is telling you the coarse-grained entropy in a particular precisely defined sense. Yes.
Okay, thank you.
But I think you want to stress that in certain situations, the generalized entropy is really the fine-grained entropy.
Yeah, exactly. If this becomes the minimal quantum extremal surface, then it's the fine-grained von Neumann entropy. So for evaporating black holes, after the page time, the generalized entropy of this QES does give you the fine-grained von Neumann entropy. That's what gives the second half of the page curve, where the entropy goes back down. But for the non-evaporating black holes, thinking of then it's giving a coarse-grained entropy.
Okay.
Okay.
It just comes down to whether it's the QES. Yeah. Sorry,
Jeff,
reiterate once more, what matters is whether it's the minimal generalized entropy QES or it's not the minimal one. The minimal one determines the fine-grained entropy. Non-minimal ones can determine coarse-grained entropies. Lenny?
Yes. Let me come back to the Bouland et al. Story. I'll let, if we don't get the, if it doesn't work, we'll do it offline. Okay. So we talked about these operations taking place and what happens if you don't know what took place. Then, of course, you generate a density matrix. But somebody may know what happened. So let me set it up as follows. You just have a bunch of extra qubits. The extra qubits are in some state, alpha up plus beta down or something, and they apply some controlled operations. The controlled operations, if you're up, then you apply this thing. If they're down, you apply something else. Okay. So at the end of the day, what's going to happen is the black hole is going to be entangled with the register being these extra qubits.
Absolutely.
All right. Does it now? All right. So now we have the black hole entangled with a whole bunch of stuff. Has it reduced to the same issue as the issue with Hawking radiation?
Yes.
Instead of Hawking radiation, you have become entangled with the register, we'll call it the register.
Yes. Yeah.
That's it. That's the whole story.
At that point, it essentially becomes the evaporating black hole story. Yeah.
Okay. Thank you.
Cool.
More questions, please? I saw somebody raised hand, but hands disappear.
I have one more question.
Okay, please, Dima.
So I have a question about the story about unrestricted complexity. For example, there are different ways and proposals how to compute holographic complexity, for example, some subregion or something like that. And typically they are based on the notion of just a canonical RT surface. Is it possible somehow to define a restriction of complexity for just canonical formulations of holographic complexity? For example, just take a planar black hole and some subregion and calculate something with some restriction, or in tensor network.
Yes, absolutely. And in fact, that's a significant part of what we were interested in the original Python's lunch question, right? So if you have an evaporating black hole, so a black hole coupled to a bath, and you evolve it for like a page time, then what you might call the unrestricted complexity, so the complexity of the thing viewed as an entire system, is proportional to the time that you were evolving for, right?
Yeah.
But
yes,
the restricted complexity, the time to make that state by only acting separately on the black hole and the radiation, that's the thing that's exponentially big. Okay, so how is that related to the Python's lunch story? The answer is, if we look at this.
No, my question is in fact about, for example, we define some subsystem on the boundary. Can we make the difference for some static black hole or just pure ADS? Can we make some difference with restricted and unrestricted complexity just by making some kind of CV or CA calculation?
Yes, so I think the CVCA stuff for restricted things, I feel like there's not a consensus on what the right thing is. There's various obvious things you could do. So I don't want to go too deep into that. What I can say is that if you have a Python's lunch for that particular subregion, right, like the QESs that you have depend on the subregion. And so if you have a Python's lunch for that particular subregion, then that subregion will, that will mean that there's exponential restricted complexity for that subregion.
It's strongly based on quantum extremal surface, and you cannot go into semi-classical description.
Often you could use the classical description. Yeah, if it depends if the quantum fields matter, right? Like for things like black holes at late times, then the quantum fields matter a lot. But you could just imagine some classical space-time geometry and then you could just ignore the quantum corrections and just look at ordinary classical extremal surfaces, and the same story would go through.
Okay. Okay, and another short question. Can we consider Python lunch as a kind of giant operator, for example, in the sense of operator size, or for example, giant graviton or something like this? Is it possible to consider it in this way,
It's
or
an
this is
interesting
just
question. Is Lenny still in the chat? I feel like he'd be the better person to answer it. I would say
Well, I am.
no.
I am.
But yeah.
Yeah. Not that I know
You're
of.
much more of an expert on giant gravitons than me. I would say no, they're different, but they're both.
I would agree. I would agree with you.
I don't think a giant graviton is like that complex, right? It's certainly not exponentially complex. It's big, but
No,
it's not that
not
complex.
at all. No. No.
or in the sense that just operator of giant size is sitting in the center of some kind of wormhole, for example?
I don't
think
know.
in
I never. Go ahead.
Yeah.
Never thought about it.
Okay.
I don't see any
Yeah,
connection.
I think operators inside of Python's lunch are just much more complex and like messy than something like giant graviton. A giant graviton is just like a determinant, right? That's some pretty simple thing.
Yeah.
Okay, thank you.
More questions, please? If there is no more questions, thanks, Jeff, for wonderful, great talk. Thank you very much. It was very stimulating. Thank you.